Welcome to this nice little video about sequences. I want to share with you a variety of different patterns, and so we'll start first with some easy ones. The pattern AB, 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 AB. Hopefully you can imagine what's going to come next after this, and you're saying it's going to continue AB, AB, AB. Obviously the pattern with the shapes, circle, rectangle, circle, rectangle, circle, rectangle. If we just continue that pattern, we're looking at another circle and another rectangle and so on. If you look at the pattern with these cards, we're looking at a king of clubs and a queen of diamonds, a jack of clubs, a 10 of hearts. Hopefully you're saying that the next card is the 9 of clubs, and then probably we're looking at an 8 if we go back to this pattern of diamonds. Notice I didn't try and draw a club. So that's all well and fun, but let's see if we can link it to some math. What about if we have a pattern like this? 1, 2, 3, 4, 5, 6. Hopefully you're saying 7, 8, 9, dot, dot, dot. Okay. 2, 4, 6, 8, 10. You're saying 12, 14, 16, dot, dot, dot. But these ones start to be more complicated. 5, 8, 11, 14, 17. Hopefully you can see that we're increasing by 3 each time, so this is going to become 20, 23, 26, dot, 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 16, 12, 8. This pattern is decreasing by 4 each time, so this is going to be 4, 0, negative 4, dot, dot, dot. And so what we have here, when we started to look at these patterns, notice I started talking about the differences between them. This was an easy one. This was just adding 1 each time. This one was adding 2 each time. This one was adding 3 each time. And this one we were actually subtracting 4 each time. So the difference between each of these was what we used to find the next numbers in the pattern. So these type of patterns have a special name. These are called arithmetic sequences. And this is a case where we use the word arithmetic as, I guess it's as a noun or a verb. When we use it in a different way, we say it differently. So this is an arithmetic sequence. And arithmetic sequences, all of the terms, each item in the sequence is called a term. Terms have a common difference. So you are adding or subtracting to get the next term. For example, if I start with 31 and I tell you that my common difference, my D, common difference we can call D, is equal to 5, then you know that my next term is 36. 36 plus 5, 41 plus 5, 46 plus 5, 51, etc. Because each term here I was adding 5. That was my common difference. Well, that seems pretty straightforward, and hopefully in your head you're always saying, oh, this seems pretty easy. So let's take a look at these ones. 1 to 2, 2 to 4. Well, that one doesn't seem like I'm adding something each time, and I'm not subtracting. So how am I getting from 2 to 4 to 8 to 16 to 32? Do you see that we're multiplying by 2 each time here? So we're not going to add in this type of sequence. In this type of sequence, we're going to multiply. Hopefully you can see here that we're multiplying by 3 times 3. Here, 81 times 3, sorry, is going to be 243, dot, dot, dot. Here, it looks like I'm getting smaller, and folks' inclination is to say that they're dividing, but I'd like you to think of this as not dividing, but multiplying by a fraction. So what fraction can you multiply by to get a smaller number? In this case, that's exactly half. Then we're going to multiply by 1/2. And 50 times 1/2 is 25. And 25 times 1/2 is 12.5. Dot, dot, dot. So in cases where you have sequences that are multiplying, we have what we call geometric sequences. The terms in a geometric sequence are connected by a common multiplier. Something we're multiplying by each time, and we're going to call that also known as a ratio, which is why we use the letter R to talk about the common ratio or common multiplier. What are we multiplying by? So you multiply to get the next term. So for example, if I say we're starting with -2 and our R, or common ratio, is 3, then I know that -2 times 3 is -6 times 3 is -18 times 3. This is where you're leaving me. I think that's 54, but I'll double check that for you in a second. I was right. 18 times 3 is 54, but I forgot that it was -18 times 3, so it should be -54, and so on and so forth. So, if we want to put a little formula with our sequences, we can do what's called a next equals now formula. And basically, how it works is to get to the next term in our list, we take where we are now, what term we're at now, and we, if it's arithmetic, add or subtract something to that term. If it's geometric, we're going to end up multiplying something to that term. So if you look at this example, it looks like this is the one from earlier where we were adding 3 each time. So to get to the next term after 17, to get to the next thing, which would be right here, or I can write it out like this, next equals take where I am now. So this is where I am now at 17, and I want to add 3 to it. So I'm adding 3 to 17. That would get me 20. My equation just stays as next equals now plus 3, and I say start at symbol. I'm going to start with the first term in my sequence, which was 5. Whoops. In a geometric sequence, this is the one where we were multiplying by 3 each time. And so to get to the next term, I'm going to take where I am now. So next equals now. And I'm doing times 3, start at 3. Let's take a quick look at some other types of sequences. If you look at this one, it looks like we're adding 3. But then, actually I'm going to do it down here so I have a little more space, plus 3, but then this is actually plus 9, and this is plus 15, and this is plus 21, so there's not really a pattern there, but if you do go out one more layer, you can see that the difference between all of these is 6. And so since we're finding the common difference at the second layer, this is a quadratic sequence. And I'm only introducing that to you, so if you come across a situation like that, you know about it. You don't need to worry anymore about it. So it's a quadratic sequence. It's neither arithmetic nor geometric. This sequence might be one that you're familiar with. If you notice, 1 and 1 gets you 2, and 1 and 2 gets you 3, and 2 and 3 gets you 5, and 3 and 5 gets you 8. This is a special sequence called the Fibonacci, F-I-B-O-N-A-C-C-I, the Fibonacci sequence. And that mimics patterns that we find in nature and naturally occurring things. So the Fibonacci sequence is a famous one. So quick check here, take just 15 seconds and see if you can figure out whether these are arithmetic or geometric or neither. And I'll pause for a second. If you look at this one, it looks like we are minusing 4 each time, so this is going to be an arithmetic sequence, and the common difference is -4. If you look at this one, it looks like we're adding 7 each time. Does everyone agree with that? And so that's also arithmetic. And the common difference is 7. Here, I don't see a regular pattern. If you do the first one, it looks like it's adding 7, but this one looks like it's adding 8, and the next one's adding 9, and then 10. And then if you look at all of those differences, it's 1 between each of those. Remember we said that that's going to be, when you find the differences at the second level, it's going to be probably a quadratic, but since it just says arithmetic, geometric, or neither, we'll just say neither. 8, 24, 72, 216, that's looking like multiplying by 3. So that's going to be geometric, and the common ratio is 3, the common multiplier. And let's see, this is one of those multiplying ones where it's getting smaller. Can you see that we're multiplying by a half? So this is also a geometric sequence with a common ratio of 1/2. That is it for me. Why don't you try and make your own sequence, starting with 12 for each of them, and filling in 5 spots. So come up with whatever your common difference is going to be and whatever your common ratio or common multiplier is going to be. And we can share those in class. Thanks for listening. Have a great day.